Today we're going to do the 863 question of the Leetcode, which is all nodes distance k in binary tree. So let's read the question first. Given the root of a binary tree, the value of the target node target and an integer k, return an array of values of all the nodes that have a distance of k from the target node. You can return the answer in any order. And let's try the constraints now. The number of nodes in this tree range is 1 to 100, 500. So there will at least be one. There will be at least be one node in the binary tree. So we don't have to check for a null binary tree check. And the node value can range from 0 to 500. And all the no values in node.value are unique. So we don't. So that's good. So we don't have to worry about multiple nodes having same target value. Target is the value of one of the nodes in the tree. So there will be always be a target in one of the tree, and k could range from 0, which is the target itself, to 1000 depth. Okay. So let's understand with an example first. What does the question say, or what does the question ask us exactly? So let's draw a binary tree of 3, 5, 1, and another 6, and 2, and 7, and 4. Okay, and we'll take the arrows and we'll draw this, draw this, draw this, draw this, and draw this, draw this, and value is 3, 1, 5, 2, 7, 4, 2, 7, 4, and 6. So let's first understand what do they mean by distance, right? So what is a distance at all? So the target node we've been given a target node, and we have to travel from we have to find nodes with the distance k. So what is a distance exactly? Distance is nothing but an edge, or the number of traversal it takes from one node to another node. So the number of travels it takes it from 5 target node to 2 to reach another node 2 is 1. The number of traversal it takes from 5 to 2 to 7 is 2. Again 5 to 2 to 4 is also 2. This is the distance, right? And we've been given a k. So we've been given a k. K is some number, and we have to find all the nodes with that are k distance away from the target node. Got it? Okay. So now we have to, so let's say this is pretty easy. So from the looks of it, this seems pretty easy because we've given a target node. We can just apply a DFS approach where we say key, once we move on to the next node, we'll increment the distance 1, and from there we will continue to increment the distance. From here the distance is 1, so 1 plus 1 is equal to 2. Again 1 plus 1 is equal to 2. So we found two nodes that are children of the target node. But if you see from this node, the distance between up to this node is 1 and 1. So 1 plus 1 is equal to 2, right? So how do we get this node, right? In case of children, we could just use a DFS approach and use a distance counter and reach until we get all the nodes with distance of 2. But we cannot go from no children to parent in binary tree. So there's no pointer here as such that we can reach from children to a parent. So how do we do this? Well, I think I've pretty much explained the question, and the solution lies in front of you. So what if we don't have a parent, if we don't have a pointer from the children to parents such that we can traverse from here? If there was a way to traverse from here and to go here such that we can say we can keep a distance counter from here and go to the parent and go to their children and see we can increase the distance here too. So 1 plus 1 again is equal to 2. So what we can do? Well, we can just, if you think about it, this is sort of like a graph problem. So we can just create a pointer from all the children to its parent, right? Each children can have only one parent since it's a binary tree, right? So we will make this point of this, and we make this node point to this, right? So now we can see from the target node, we can travel from here to its parent, and we can also look at its children, right? So we can go to all nodes with, we can now traverse to all, we can traverse both the bottom of the children target node and the top of the children node, such that we can find a such that we can find all the nodes with distance of k. Okay, so what kind of approach can we use here? Well, we can just simply create a graph map where we first use a DFS or BFS approach, BFS or DFS approach, to get all to map all children to its parents, right? So let's start with parent. Okay, so let's start with DFS from root approach. Okay, so I'll start from 3, and is there any parent of 3? No. So I'll go to the left and right of it. Before going to the left and right of it, I'll pass 3 as their parents, right? Node 3 as parent. And when I come to this node, I know there is a parent of this node, so I'll say, in my parent graph, I'll say 5, and 5's parent is node 3, right? And when I come to this node, I say the parent of 1 is node 3, right? And same for this one. When I node 3, when I come to this node, I'll pass 5 as the node in a DFS approach, and I'll say the parent of 6 is node 5, and 2 and 2's parent is node 5. Again, we will use the DFS approach from this node to this node. I'll say 7's parent is node 2, and 4's parent is node 2, and yeah, that is it. We've now built a parent child graph. Okay, now that we have built a child parent relationship, how do we solve this problem? Okay, let's start from our current let's start from our target node, right? We know that targets node children, so we could always go down, right? We could always look at the children. Now we can also look at its parent, right? So initially, let's keep a pointer of distance. Let's keep a pointer of distance is equal to 0, and q, right? We will use a BFS approach to travel. This is exactly a graph problem. We'll keep we'll give a q, and it will initially have a target node, which is 5, right? It will initially have a target node of 5, right? So I'll now I have nodes in the queue such that the distance between the target node and the current node is, all the nodes in the queue is 0, right? Since the the distance between the target node and target node is essentially 0, we don't have to traverse from target node to anywhere, right? But what I will do is now take its children. So let's build a queue here. So I took 5. So I took 5. I took 5 and I crossed it out. I took it out of the queue, and I got its children, which is 6, and sorry, which is 6 and 2. And since we have it in the parent map, what's the parent of 5? Well, it's node 3, so we will insert node 3, right? I'll just move this away. Let's move this here. I don't know. Let's move this here and pan this out, and move this here. Okay, so let's move this here. Okay, and node 6, since we have it in a parent, so what's the parent of node 5? Well, it's 3, so we insert 3 node 3. So we insert node 3 in the queue. Okay, so we now have traversed all the nodes with distance of 0 from target node. Right now, we are going to traverse all the nodes with the distance of 1. So we've got all the nodes in the queue are from distance of 1. So this is distance of 1. So this is distance of, so this node is distance of 1, this has node distance of 1, and this node has distance of 1 from target, right? Target node, right? So we have, so in the queue, in the queue, we have got all the nodes with the distance of 1 from this. So we can erase this and increment it to 1, right? Now we will traverse all the nodes with distance 1. Since the distance is current distance is less than k, we have not traversed up to all the nodes with distance of k. We have to further get this get these nodes children, right? So I'll go to the 6. I'll take the first node out, and I'll say 6. What's the neighbor? There is no left, there is no right. Oh, there's a parent, but we have already traversed the parent. Why do I have to traverse parent again? So I could just maintain a visited set too, where I once I considered it, I'll always add it to a visited set. So 5 is my visited set now, and there's 5, and there's 6, and there's 2, and there's 3. So this is like a normal graph problem where you say ki you want traverse the array again. Okay, so now we want traverse these array again. Okay, so we got 3, 2, 6, 5. So 6 children, there is no children, and the parent is already visited. I'll take the next node 2. There is a children. I'll add 7 to queue and 4 to queue, right? 7 to queue, 4 to queue, and there is also a parent. 2's parent is node 5. 2's parents is node 5, but it's already visited, so I don't have to visit again. So I can get rid of this. And there is the node 3, the currently node 3. I'll look at the children. Children is 5, but we already look at the 5. It's already in the visited set, so we don't have to visit it again. And while I visit it again, and there's another children 1, so I'll add it, right? Add it to the queue, right? And I'll add all of them in the visited set, so I don't visit them again in my pursuit of nodes with a distance of k. Okay, got it? Yeah, got it. Now I've got the nodes. Now I have got the nodes. Now I've got nodes in the queue with a distance of 2, since we got the children of nodes with a distance of 1 from target node. Okay, so is the distance is equal to k? Yep. So we can just return these nodes values. Yeah, I think this yeah, that is it. That's the solution. You just have to build a graph. To sum up the solution, you just have to build a parent child graph, and from target node traverse up to kth node, both bottom and up. Now, I'll be using what will be using? I'll be using a DFS and BFS approach, and let's talk about the time complex. Okay, so we'll talk about the time complexity and space complexity at the end of the video. I'll just come back to the code now, and I'll show you the code. Okay, let's take a main function, which is kth nodes, let's say, and we'll take a root and a target node and a k, right? First I'll build a graph. So I'll write another let's just build a graph. Let's say parent graph, and this will be initially empty degree, and I'll say def dfs and build graph. Here I'll take the current root. Here I'll take the current node, and I'll say parent node. current node and parent node, right? And if there is no node, if not node, return none. And if there is if the parent exists, if a parent exists for a node, only then update in the parent graph that node dot val has a parent graph. And do this for the for nodes left nodes, and parent will be node. The left nodes of the node will whose parent will be left, and right node of node will have parent node. So I'll just call build graph. This will give us parent graph, which this will give us a parent graph relationship, right? Now I'll approach a BFS approach. I'll take a queue and take a visited set where I'll initially in the queue I'll initially set target, and in set also I'll set it as target dot value. Since values are unique, set can be used to, instead of appending the nodes, we can just use the values in visited set, since the values in the node are unique according to the constraints, right? According to the constraints. So what I'll do is I'll take a distance. Now I have all the nodes in the queue with a distance of 0 from target node, and I'll say while queue I'll say if distance is equal to k. If yes, I'll say if the distance, I'll break out of the loop, and I'll say if size is equal to length of queue, so that I just traverse all the nodes with current distance now. So I'll take all loop through all the nodes, and I'll say if node dot left exist and node dot left dot val not in, if the node dot left dot val not in visited set, I'll take the node out of queue by popping the first element. If the node exists and node dot left dot val not in, if we have not visited the element again, I'll say queue dot append node dot left, and I'll add it to the visited set. We did visited dot add node dot left dot val, right? And I'll do this for right and my parent, right? I'll do this for right, rigst, and I'll say if node dot val in parent graph, and parent graph node dot val. If the parent's value is not in visited, only then take the parent graph's node's parent, right? And add it to the visited set, parent graph node dot val, right? And at the end of the day, once I break out of the loop, once I get all the nodes with distance k away from distance away from the target node, I'll say while queue I'll take a result value. Since queue now contains the nodes, not the values, we have to take a separate result array, and while the queue is not empty, result dot append queue dot pop all elements and get its value, right? And just return result, right? And what I'll do is call kth nodes. I just have to pass root here and parent as none. Parent will be initially none, right? And if I just take the code, pasted it to Leetcode, if I just take this code and pasted it to my Leetcode, I'll just check once. I took a parent graph, I said I built graph. If there is no node, return none. If there is a parent graph, build graph, and build graph with node right, and I'll say build graph. Q is equal to target, visited equal to target dot val, distance will be 0. Oh, I forgot to increment the distance. This is why you always check code once, right? Even after you write, if you thought through, return everything, you just have to go through the codes once just to see it's not a good look in front of the interviewer that you have written all the code and your code won't run without checking. You're going to run the code and it's going to end up in error. I just hope this doesn't error it right now, because I hope it works out. When I built a parent graph, I set it as, instead of setting it as parent, the node's value is a parent, I set it as directly as parent graph, so I changed that one. Another mistake was I incremented the dist inside of the loop instead of outside of the loop, because I do it outside of the loop because I have to increment the distance only when I have traversed all the elements of the previous distance. Yeah. Yeah. Right. If I should run it, I should have a correct answer, and if I submit it, it should submit successfully. Yep, that is it. Beats 10% of the users, and yeah, that is the of this code. Let's go back to the diagram code. So what do? We first write a DFS solution to convert a binary tree from binary tree to sort of a graph, and then do a BFS approach, and to find out to traverse up to the kth nodes. We keep a result array to get return all the values. Usually in Leetcode, the the resultant value is never considered as an extra space, so we won't consider we won't we and even and we won't even consider it, and even we won't consider it too. Let's talk about the time complexity of DFS. The time complexity of the DFS is O of n, since in the worst case we traversed all the nodes in the array, and the space complexity is height of tree, right? Same for the BFS. The time complexity is O of n, and the worst case space complexity is if you have all the nodes in the queue, which is O of n again, right? Right, and the space complexity is height of 3 will be n by 2, right? I'll just write the time complexity. Time complexity is O of n plus n, which is 2n, and space complexity is 2n. So it's just basically as time complexity is O of, and as space complexity is O of n, right? Yeah. Yeah, so yeah, that's it for the today, and yeah, please share, like, subscribe, and I don't know, go crazy.